Okay, so Levi's not here, so I'm going to try to speak very clearly to him. Hi, Levi. He better watch this video. Okay, Alvin, make sure he watches this video. Okay, so I want to. Can I get a raise of hands? Who can give me a charade for number 1? Okay, go for it. How does temperature? Shh. This is a silent charade. We are the audience. We're watching them. They can talk. You guys are fine. So how does temperature play a role in rates of reactions?
We had it, but we didn't realize it's silent.
No. You guys are fine. You guys are fine. I said them be quiet.
Oh,
yeah. Let's go. Let's go.
So right now we're moving at like a certain rate right now, and we're kind of slow. And then boom, our temperature goes up by 10 degrees Celsius, and then we're here. Oh my gosh! We're doubled, and now we're doubled, and we're faster.
Oh, okay. Woo! And then they decrease by 10 degrees and they're back by.
And now we're
Okay, so they're calling themselves a rate, but we would have to measure rate a little differently than piggyback style. But you know, we could realize that increasing by 10 degrees C does what to the rate? Doubles the rate. Okay, the rate of a reaction. So why does temperature play a role in rate? It's all about collisions, right? If you don't say the word collision, you're doing it wrong. All right, so it increases the number of collisions. At this point, it's apparently looking like it's increasing the collisions. But this 10 degrees change will cause the collisions to double, which then hence the rate would then double as well. So it's something about collisions. We're going to talk about sometimes how that linear relationship of doubling the temperature, doubling collisions and doubling the rate doesn't necessarily mean the rate will double. We'll talk about like orders and stuff shortly. Can I get a catalyst? Do I have a catalyst? Okay, go for it. If I don't get volunteers, I volunteer, so I'd really rather not volunteer. All right, team, let's go.
For application, I'm the catalyst.
Okay.
And I lower
lower the activation energy. Okay. So the catalyst is manipulating activation energy. How? Like, how does that work? It's a good question. It's okay if you don't know. It wasn't? Okay, so it's speeding up the reaction rate by, does anybody have anything to add to that? Yeah?
Altering the reaction pathway.
Altering the reaction pathway. Okay, so back to your seats. I'm going to kind of draw that here first. So catalyst plays a role by lowering the activation energy. EA is activation energy. Who remembers seeing that in honors chem? EA, activation energy. Okay, so it lowers the activation energy, which causes the rate of reaction to increase, is what they said, and that's only going to occur if there's an alternate mechanism of reaction. There's a different type of reaction in the middle that's occurring. But before when we did thermochem, we were like, we care about the beginning, we care about the end. I don't care what happens in the middle. I just look for the final and initial. Now we're like, ooh, what's happening in the middle? That's what we're talking about now. So we said in the middle there's a different mechanism or a different pathway. How Avery read it for us, right? It's a different mechanism or a different pathway. Okay. What constitutes an effective collision? Thank you. AJ and Kirk. Yes, Kirk. I got five questions. I got kind of 5 groups. This is going to work. All right, effective collision. We're watching you.
So we have 2 molecules or 2 atoms. These are valence electrons.
Okay.
They will repel each other, but will move towards each other with enough energy to overcome that.
Oh, I thought you guys were going to hug. Okay, never mind. So, overcome some sort of boundary. And, okay, so we're saying electron-electron repulsion could be a boundary. That could inhibit some sort of collision. I'm actually going to add to that too. So, constitutes an effective collision. There's 2 factors. You guys got 1. So, I'm going to say collide with enough energy to overcome some sort of barrier. And so that barrier could be identified to be activation energy, some sort of repulsion, maybe even the states of matter being so different that it can't effectively collide. Okay, so we're saying collide with enough energy to overcome a barrier, activation energy. There's one more factor. Okay, I think that's going to be really intertwined with this energy aspect.
Correct orientation.
Right. So can you guys collect what's the incorrect orientation for me? Let's go quickly, please. Okay. So if you don't collect correct orientation, you're just not going to react. So incorrect orientation, go. There you go. Yep. Just bounce off each other and go back. Right. So come on, Chloe. Get up here. All right. So this is the bro bump. We're not gonna chest bump. We're just gonna self bump. Woo! Okay, so that's effectively we made a new bond, something like that, right? We were able to collide to create the correct bond. So energy and orientation are two things to consider for effective collisions. If one happens and the other doesn't, the reaction's not going to occur. All right, two more. How do you calculate instantaneous rate? Can I get a different little couple? Come on, Sean and Binky. If you got to pull Alvin, Alvin is also available. He's available. Instantaneous rate. Okay, ready?
This one's kind of a struggle because it's like kind of a 50 graph, so curve it
Let's do this.
So I like want to find like the slope like around like this area.
Yeah.
It's like
Okay. This is like practical yoga. Okay, come on. I have an actual here. Let's go. So what have you done, Vicky?
on the slope of the bungee.
Of a tangent line. Okay. At one temperature. That one temperature was. That one time was right there. Or you go here. Or you go here. Or you go here. And now we go to the left side. That instantaneous rate, just hold on to that ruler, sorry. Okay, so the instantaneous rate is going to be at a time, which on this, with respect to this, is at a specific time, and we would find the slope at that, slope of the tangent at that point, and that for us is rate. Now, I briefly heard you guys say the rate you traveled to school today, which was some number blank. What else? So, but you said miles per hour, right? So you did miles per hour. So in everyday life, our rate is distance per time, right? But in chemistry, do our molecules really travel a great distance? No. So what were some ways you read about that could notify us of some sort of change over time? So we don't really measure distance, we measure other things. So you can measure like rate of bubbles. So, but I can't really count those bubbles, right? So it would be a better way to measure that. Bubbles have a volume, right? So you could do change in volume over time. That could be one way. What else? I heard this group.
Concentration.
So how do we measure concentration though? Good question, right? How do I measure concentration? Can I just look at this and go, that's about 2 molar. Yeah, about 2 molar. Yeah. Okay, so the concentration must be something that's colorful, right? Like I can say, oh, it's light blue, it's dark blue. Well, that's a qualitative way to do it, but I also could throw some light through it, look at the absorbance, look at the transmittance, boom, Beer's law, boom, concentration. What's Beer's law? A is equal to ABC, so I think ABC store, okay, Beer's law. This is what? That's how you remember. That's how I remember. How else do you guys remember that? You memorize it? Oh, this is what I've remembered it from since I was 10th grade or whatever. Okay, so this is absorbance. Sorry, you gotta come up with your own ways to remember things. This is what? Little a, pequeño a, ah. Okay. It's molar absorptivity. Okay, molar absorptivity, I abbreviated that. Okay, what's B? Cuvette length. And that's usually in like centimeters or so, like 1 centimeter, we usually our approximation for that, or 2 centimeters. We usually don't have to calculate that ourselves. We just know that we use the same cuvette the whole time during these experiments, so we don't have any differences in our measurements. And then this guy is our concentration, right? So yes, change in concentration could be measuring absorption over time, and that would then be correlated or directly related to the concentration change over time. That's about it. There's a couple more things we can measure, but those are the two that we could measure most definitely. Okay, so how are relative rates different than instantaneous rates? Look at your notes for that. this is a little hard to charade out. Does anybody have something that can add to that? You guys are just lively today. Relative rates. Go for it, Arushi.
I mean,
No one else knows, so whatever you say is probably great.
what?
Go for it.
Okay, well, if you, I was gonna give like an example, like you said with the cars.
Okay.
So if you won't drive the same speed, like every single time, like
Okay.
the whole time. You'll have different speeds.
Okay.
So at the instantaneous rate, that's like what your speedometer says at a certain point.
Okay.
But when you do the relative rate, when you do the relative rates, you're looking at it like over like a certain period. So that's like taking you slow. So that's x1 minus like x2 y2 minus y1 x2.
Okay. So relative could be over all time versus at a specific time. That's a good point. So over the entire length of the time, the relative rate could be, I would call that, when you're saying relative rate, I would call that average rate versus relative rate, because that's your average speed or rate of reaction over time. With me? Okay. This also could be like, okay guys, we're talking about reactions, right? Over time, what's reacting? It's not a hard question. The reactants. Okay. What's being produced? Products. Relatively, the rate could be basically like talking about consumption versus production. So the relative rate of, let's go hydrogen gas plus oxygen gas makes water. Is this right? Nope, that's not right. 2 right there, that's 1. Okay, so the relative rate of reaction would be as H2 is consumed, the rate of production of water is equivalent, right? Because it's a 2-to-2 ratio. But relatively, the rate of consumption of oxygen is half of that because it's a 1-to-2 ratio. So it also could be not only looking at it over time, but also stoichiometrically as well. Okay, so that's kind of a quick introduction. Those are some of the basics we'll kind of talk about today. So I have 2 questions. This is one of my game plan ones. I have some notes and some examples I like to do. I do want to start you off with one video first, and then there's a little simulation. The simulation is going to break into groups, and you guys are going to kind of talk about it together. There's also it's called All Screwed Up Lab. It's just a hands-on activity that kind of helps you with understanding orders. But I need to do that towards the end, because we haven't really talked about orders yet. So starting off with the video, and then I'll ask you about how much of the simulation you guys want to do today. I'm all about that fun Friday right now. Okay, so we're gonna try to see where we are. So you may have seen this video.
Yeah.
Okay, we did, but I'm going to quickly review with you. Add this to your notes, but this is the stuff you should know. And really, I'm doing this for Levi. This is for Levi. Write down the factors that they talk about the rate of reaction.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those 2. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen.
All right, sorry.
Second, I propose increasing the overall population of the school. More
When it doesn't pause when you click it, there's probably those markers over there. Okay, so the part that you should be writing down are the individual change and how does that change impact the collisions. You have to say the word collision if we're talking about rates, because that's basically what's causing a reaction curve. Things have to collide, they can't just react without collisions. So if you write them now, we won't write them later, so I'm trying to kind of help us with our notes today.
more students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing.
Okay, so that was a two-part one. He's saying it pretty quickly, but just a quick review. He said decreased volume, or volume of the reaction vessel. So that increases collisions because why? There's less room around, so they're likely to collide. Frequency of collisions increase. Increasing the concentration, which he said number of people. Increasing concentration means they're in closer proximity. The collisions then just naturally should increase. Moving quickly, he said increasing velocity. You know velocity or speed is directly related to kinetic energy. Well, kinetic energy is related to temperature. This is a two-part one though. He said increasing the temperature does what to the particles? Okay, so they move faster. So if they move faster though, tell me about how that impacts collisions. Kurt?
It's like more energy.
So more frequently, that's one thing. And then more energy, which means they're most likely to meet the effective collision criteria of enough energy to meet activation energy. Got me? That's the only one with a two-sided part. So move faster, increasing frequency, and increasing energy of collision. Okay.
Collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? And a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
All right, so that's, I think, very commonsensical. Who feels good about that? Thank you, thank you. Okay, so here's what, I'll do the simulation in a second. I do think, let's go to that part that he just spoke of. Here's the additional information that relates to what we just wrote down. There's just a couple of things I just wanted to identify here. Basically, we know how rate can be affected, basically we know how it can be sped up. So the only other things that he didn't speak of was basically, can they actually collide And is that thermodynamically favorable as well? So the nature of the reactants is important to consider. Sometimes one reactant and other reactant are just so stable. If I try to react them, they might collide and then reverse. So the rate of reaction would be basically nothing because the reaction did not occur, or it's not measurable enough to occur. So sometimes you have to think about the thermodynamic favorability. What gives us a thermodynamically favorable reaction? This is variables. You just had this test yesterday. What a variable represents this? Delta G. Delta G has to be negative, and that could correlate with different enthalpy and entropy values as well. It also could be just related to the complexity of the bonds. So sometimes very complex bond structures kind of limit the likelihood of a reaction happening because you really have to have quite a bit of energy to overcome the energy of those bonds. Remember, karate chop those. And it sometimes takes a lot, and it may resist reacting some. So the surface area aspect, which he spoke of being impacts, right, does impact the ability of collisions to occur. So that's why this is my favorite example, because you guys did most of you did maybe not. The penny lab where you took zinc powder and a penny and an alloy that looks like a gold penny. So zinc powder is really flammable. If you rub it between two paper towels, the paper towels will catch on fire. But zinc strips, you're like, okay, it's not going to catch on fire because it's a solid. It's not powdered form. The physical state can definitely impact it, and that's because if I'm talking about overcoming the energy barrier, which is the activation energy, the kinetic energy of the particles has a play in that. So if you're trying to meet the two criteria for effective collisions, EC is effective collisions. You're trying to meet those, and you're using a solid. You're like, okay, solid. Solid. It doesn't matter if I collide them, right? They're not going to react because they are very low energy. You have to heat them up, or you'd have to melt them to liquid form so they could start to collide better. Orientation we did speak of, and I'm going to show you what a transition state looks like in just a second. Concentration is just talking about increasing the frequency of collisions. The temperature part I did tell you was a two-part process where frequency and energy is increased, and then that rule of thumb, which Jack and Jacob so elegantly demonstrated for us. The increase of 10 degrees should approximately double the rate of reaction. All right, so then the catalyst part is the only thing that we've not spoken of in depth. What's another word for a catalyst in biology? Enzyme. Enzymes they're what basically allows us to survive. There's no way we would even be able to create enough energy for 30 seconds or so to live if the enzymes were not there, ATPase and so forth. So enzyme is a good example to make sure you write down, because that's not one that we extensively talk about, but they are going to be some in your problems that you'll see. So if you've not drawn something like this in your outline, this is something that you might want to describe, and then we'll kind of label the activation energy differences on both of these fronts. And I might go probably about 5 more minutes, and then I'm going to have you guys start the simulation for a second. So I'm going to have you guys get laptops periodically. So do a couple here. And remind me to make sure the part that was not identified in the video, and it was in your reading. It definitely was in your reading. So if you guys like kind of are taking notes on your reading and starring things, the thing that was mentioned is that catalysts are not changed. They are reusable. And they're not consumed, so they're still there. So they still exist in the reaction vessel. You guys can have your laptops too. Okay. And so in a reaction in your body, it would be pretty impossible to keep up with the demand of all the enzymes you need for all bodily processes and mechanisms of digestion and everything. It would be impossible if you destroyed your enzymes after every single use. It would be very, very energy inefficient. So just like our bodies reuse enzymes, we can reuse enzymes. So one of the questions that was highly missed on your redox test was what happens to the H plus, the acid component. Gosh, I forgot the exact question was, but basically it was like, what happens to the acidic component of the reaction? Well, supposedly our acid is our catalyst, right? And that's what we use to speed up different types of reactions in redox. So the H plus in that particular example of redox would be our would be our catalyst, so it would still exist. But if in a reaction I'm making water, water is just a liquid, right? What does addition of water do to my concentration of anything? It dilutes it, right? So something, if an H plus is diluted, remember this is acidic. If I dilute the concentration of H plus, and this is just a side note for us, okay? pH is equal to negative log of H plus, and I dilute this concentration, what happens to my pH? It goes, because of negative log, right? So it goes more basic. That was one of the Highlands questions, and I just thought I'd mention that one. Well, I'm here because it relates to the non-consumption of our catalyst. Okay, so on this graph here, we have free energy on this axis. It can differ, but I'm going to speak of free energy right now. So initially, this is energy of the reactants. This up here is our energy of products. And so we labeled this to be what yesterday on our test. Pretend this is potential energy, sorry. What is this? Delta. This is our delta H, is our enthalpy of reaction. You can see it's positive, right? Positive is endothermic. So you can see that. But on top of that, you also have to know now, like earlier we kind of ignored the stuff in the middle, now we are talking about the mechanisms in the middle. The energy that the reactants have to put forth to meet this transition state is quite a bit. So energy from here, I'm going to label this in a different color, to here, to the activated complex, that's what it's called, or the transition state for some examples. That's quite a bit of energy, and that is the EA, the activation energy. So, does that make sense now, as you compare it to, I don't have one up here on the board. Actually, I will draw that right now on the board. Kind of draw it kind of small, maybe, to the side. So an exothermic reaction is like this, right? Look at that little bitty activation energy. It's so small, right? So why are exothermic reactions most likely to happen versus endothermic reactions? Smaller activation energy. If you can put forth a little bit of activation energy, this will be kind of like, okay, we meet our activated complex. Let's go ahead and move on. But endothermic ones are usually a lot higher, so they're unlikely to happen, which is why you don't see as many of them. Even in our labs, you don't see as many endothermic reactions. So catalyst, its job is to make that more attainable. Well, the attainability comes from lowering the activation energy, which is because there's an alternate pathway. So it is going to be yay big, not the huge part there. So we call that E sub A, or E prime, EA prime, E prime A. And that's our our energy required through the use of a catalyst. Questions on this right now? Okay, last people go grab your laptops for me. All right, so the other part that is just a fact that you should realize is that a catalyst doesn't discriminate. Catalyst will actually increase the rate of reaction for both sides. So if we're going from reactants to products, or products to reactants, which is a reversible reaction. And so we'll see a lot more reversible reactions kind of coming from now until February, but they don't discriminate. They're going to catalyze either way, because all they do is they take the two reactants for those products and put them together. All right, let me go back to what I skipped here. So I don't think I need to go over every key point here because you guys did some of your reading. I'm going to leave this here for a second. Go ahead and go to, actually, it's probably easier if I put the link up here. Go to this link for me, and I'll tell you guys what I want you to do for about 15 or so minutes right now. Because it's sometimes better to see through the perspective of the reaction, or the diagrams on PET, which are the little particular diagrams, to see the impact. So I'm going to assign you guys to groups. You can work together or not. I'm going to have us only do a part of this today, though, not the whole thing today. This is actually a pre-lab for a lab. So instead of doing the lab right now, we're just going to do the pre-lab component. We have about an hour left, so we're doing great. So who's already on? A couple of us, okay. So once you get on there, it's going to say everyone read this section, and then it will break down into groups. Does everybody have the URL? Okay, hold on. Sorry, I'm getting ready to. I'm gonna try to switch screens. So this is an example, and it's trying to keep in the perspective of like marble and hydrochloric acid, which is a real life example of like statues. Statues are generally made of marble, and acid rain doesn't have hydrochloric acid in it, but acid rain has some sort of acidic component in it. And so it's talking about the kinetics of real life erosion of said statues. And for this lab, it has marble and hydrochloric acid. It also changes scenarios a little bit and talks about something else, but I want you guys to explore a portion of this. Can I go off this now? I hope so. Okay. Explore a component of this based on where it says everyone. If I can make the screen bigger. Yeah, okay. So at the very top it says day 1. It gives you a decomposition reaction. It tells you some context. And it says group 1 lists the factors through 3. And then after that, everyone. And then it says group 1, 2, and 3 again. So I think we'll get through a portion of this and you'll be able to describe what you can do. You can either write this stuff down on a separate sheet of paper. We're going to share probably on Monday. Or you can just make a copy of my Google Doc. You guys know how to do that? File, make a copy. And when you file, make a copy, you have this doc. It's yours. You can edit, you can do whatever. But you can also share it amongst the people that you're assigned to work with right now. And that can be where you put your information. Does that make sense? Okay. So I'm just going to number you guys 1 through 3 just off, and then you can sit with your groups as a whole, or you can sit with one person from that assigned group, okay? So ready? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1. Okay, so 1s go to Alvin, 3s go to Courtney, 2s. Twos come up here someplace. Maybe so you guys can sit together, or you can work individually, but I want you to start reading through that. Yes, you have to get up, ladies and gentlemen. I have to go grab your packets off the printer. I printed out these massive packets. Room, I guess they're in the printer. Yeah, I have a 25-page packet. Like, you guys can sit out loud. Move where you're gonna move. I'm really. Yeah. So read the information that says everyone, do a couple of those questions, and then move on to the group assignments. Grab those back and forth. Yeah.
It is not allowing us to
say out loud for you. I understand you did read some of this, but I want to just highlight the key points here, and then we're going to go back to the labs. So if you're in the back, you should be up here at this point with your computers. I know usually you're not just leaving your computers, but at this point, Alvin, yeah, you good? I'm done too. Okay. So the only part that is a little bit wordy is the differences between activated complex and a transition state. So they actually are two different theories. There's like the activated complex theory, and then there's transition state theory. But we're basically going to mesh them because they're kind of one and the same. So it's a hypothetical transition state where the reactants have started to collide. The products are starting to be formed at the same time, right? And so that's occurring at the place on the peak of our reaction diagrams. They're called enthalpy diagrams, reaction diagrams, potential energy diagrams. That's about all the names we have for this little schematic. But what you can see is that they were collided with the correct orientation, correct activation energy. They formed this meshed complex, and so it's called the activated complex because it's very, very high energy, right? Things don't want really high energy; they're very unstable. So point to note is that either the activated complex is able to proceed to form products, so it goes forward, or it just falls back and goes back to form reactants, but you never even knew it made itself because you didn't see a chemical change whatsoever. Right, so this would be going back to free form reactants in a reaction, or go forward to form products, and we would see the reaction. So activated complex, just note that it's the peak, the pinnacle of these reaction diagrams, but it can return back to reactant molecule state. And then there are some diagrams that just to give you a picture of what it means to be correct orientation and not. If you're trying to form N2O2, what has to meet together to form N2O2? I mean, O4, so dinitrogen tetroxide. What has to actually touch? The nitrogens, right? They have to form a bond here. Well, so the nitrogen and the nitrogen collide here, hence collision, bond formation, we make the product, but in this example, the O and the N collide, which is not the correct orientation, therefore that NO or that NN bond could never form, so that would be in a reaction. That's a good illustration of what I mean by correct orientation. Okay? Just to give you an image with that. And then we briefly spoke of this, like how do we measure, like what are the measurements we do in chemistry, because it's very different in physics. We generally will talk about concentration versus time, and we can talk about the relative mole ratios, which Arushi kind of picked up, and I kind of finished up with the stoichiometric relationships being, you can say, okay, I'm consumed twice as fast as this one, or half as much as this one, or producing a 2-to-1 ratio, kind of using those ratios involved. We're going to learn how to write rate laws later, but our rate law is like rate is equal to K times a concentration of reactant to some power. And that power we call an order. Do you just remember reading about that? Orders of reaction. We're doing that on Monday. But in real life, you know, we want things to occur at a decent rate so that we can actually achieve our end product, collect it, sell it, whatever for industry. But sometimes we have those thermodynamically favorable reactions that occur, but do we have any idea how fast they occur? Maybe not, but we know that they could occur, so we have to have a balance between thermochemistry and rates of reaction being favorable to actually get the product we want in a reasonable amount of time with very low energy. So we have to consider everything together. That's what we did. These are some more illustrations of the activated complex, meaning like that big thing at the top. That is really hard to achieve. It's hard to isolate because it's in the middle of a reaction. And so we're saying here, what's happening here, this could be 15 steps. This could be 2 steps. This could be 1 step. There are many, many, many steps in a reaction, just like you saw in your Hess's law of the summations. We had like 3 or 4 steps and you added them and canceled on both sides. So we're going to talk about mechanisms a little bit later. But tell me, I'll come right back to this. Tell me on this diagram, how many steps are there? 2, okay? We've gone from reactants to products, and then those products re-reacted. So those reactants formed products again. So these are like some of the more complex organic reactions that could occur. But if I were trying to designate a catalyst to speed up my reaction, which of these steps would I catalyze? Which step right now seems slower? Would take a little longer to achieve. Why one?
Because it starts off with lower energy and it gets.
Okay, so what are you comparing?
The middle part right there, where it kind of like goes down to the corner.
What do we label that section from beginning to here?
Oh,
Activation energy, right? Okay, so the reactants have to achieve or put forth this amount of energy on step 1, but the reactants only have to put forth this amount of energy on reaction 2 or step 2. So which is right now slower? 1 or 2, which is slower? 1, because it takes a lot more time to probably achieve that amount of energy. So if this is the slow step, we actually do call it the slow step. Did you see that in your reading? The rate determining step. So who determines the rate in this full-on reaction? Step 1 does, because it happens to be the slowest. Analogy, that would probably be me on the cross-country team if I were the track team. If I had to be the person that passed the baton, like a little relay race, or in a relay race in swimming, that would be me, guys. I would be the one holding up the race, like, I'm coming! Butterfly! Butterfly! Okay, so this guy that I swam with in high school, he looked like he was just having convulsions in the water. He was horrible. This butterfly was just like, he would just feel so much effort, and he made like this much. So much effort, he made like this much. We were like, you can do it, Tyler! He was horrible. But he was the only one that would do it. We had like 4 guys on the team. He was the only one that would even try the butterfly. Okay, so, slow step, this is the faster step, but it's not necessarily the end-all be-all. This is the slow step. This is called the RDS, the rate determining step. Okay, so some of this is background knowledge, some of this stuff you read. Okay, so this is one of the last things I'm going to do for now. This is a practice exam question from 2014 released exam. Read, think, and then answer. Don't judge me on my subscripts, I do not subscript. Any more hand raise when you feel good? Thank you. Alright, so say it out loud in 3, 2, 1. D, thank you. Okay, so what basically are you doing when you decrease the particle size? You're what? You're increasing the surface area, which is... No, this is a release. Sean, you'd be a great lab partner because you'd be the one that's like doing extra work for everybody. Okay, so no, this is going to be just a multiple choice question that's related to speeding up a rate of reaction based on our 5 characteristics of ways to speed up a reaction that we talked about. Okay, so it is D. Or if you want to do each of them independently somehow. Okay. All right, I'm setting a timer for myself because I could go on for days. 5 minutes for myself and I'm done. Okay, so some of this stuff is new. Some of this stuff you read, but depending on your memory, I would write some of this stuff down based on what you really need. I shouldn't need to tell you to write anything down. You should write down what you need to. So the relative rates of reaction that we spoke of earlier for warm-up was basically based on the stoichiometric relationships, meaning mole ratios. So as you can see, you can verbalize that as well. So for example, C, this is this example down here, C appears 3 times, because of the 3 times the rate of disappearance of A, because it's a 1. So as you're speaking of reactants, they're getting consumed, they're being used up, they're disappearing. They have a negative rate. So if I'm talking about disappearance, I put in a negative rate on it. But if it's appearing, I'm making a positive rate because this is all change of concentration over change in, or change of concentration over change in time. And that's generally going to be expressed as negative for our reactants because they get consumed, positive for our products because they're being produced. And in our rates of reaction labs that we'll do after Thanksgiving, we don't have one, no, we don't have one next week. we can measure either. Depends on which one's a colorful species. We have a species of a reactant that's purple, for example. I can measure the disappearance of purple over time, or I can measure the appearance of maybe something that's blue, formation of blue over time, which those absorbencies could be related to concentration. When we talk about rates of reaction, we do reference the mole ratios as the molecularity, which is a word we don't generally use. It's the molecularity of a reaction to kind of go into the theme of kinetics in our vocabulary. So we can use the ratios to compare. I'm going to go forward just because, okay? So this change in reactant or change in time can also be expressed on a graph. If I'm measuring the rate of reaction over time, and I'm representing my concentration of reactants, what should my graph look like over time based on concentration versus time? Give me a little sketch in the air. Should be a negative slope. Why negative slope? Reactants are disappearing. We just said that, right? If they're disappearing, they're going to have lower concentration over time. And as the time proceeds, not only, so I saw a couple people go like straight line down. So let me see those graphs again. So I'm thinking exponential. Isn't this exponential decay? Yes. Okay. Why should the slope go from steep to more gentle over time? But why is it so fast at the beginning? There's a lot of, well, no product, huh? There's a lot of reactants. Reactants are colliding, they're making products. But then what happens to the reactants over time? They disappear. So then there's less collisions, the rate slows down. There's less collisions, the rate slows down. There's less collisions, the rate slows down, and then actually gets to equilibrium. So this is, oh, dang it, my graph's way down here. Let me show you my graph as I show you this as well. So this is the graph that you would be expected to glean information from. Something like this. You should know that the graphs are going to be concentration versus time, because that's how we quantify things in chemistry. And those concentrations can be referring to reactants. In this case, this is a reactant, or it could be with a product. So products are going to be, they're going to be formed over time, right? So as they're formed over time, what should the graph look like? So when I'm forming a product, it's gonna, so initially, before the reaction begins, how many products do I have? 0. Okay? And as the reactants are being consumed, they're forming products. If it's at the same rate, but let's assume it's 1-to-1, just keep it easy. It's at the same rate. Shouldn't the slopes be exactly the same? Just flipped. Okay, so this should be a pretty steep slope formation, and then it starts to kind of calm down. I'm not probably doing this great, but kind of like that, right? So this would be product formation over time. So you just need to remember that who's controlling the reaction to begin with, the reactants, and we're going to express them as molarity, the rate of molarity per time, but they also, as they undergo reactions, they decrease concentration, so that's going to impact the slope, aka the rate. One second. So if I ever give you a graph like this, I'm like, what's the rate of reaction at 15 seconds? What is the rate of reaction at 15 seconds? What would you need to do? I'm basically asking for an instantaneous rate, right? Because I said at 15 seconds. What do I need to do? Find the slope of the tangent line that's at 15 seconds. So 15 seconds. Here, take, oops, that's kind of a tangent. Take your tangent. I'm going to go back to the 10 and down to the 20 because I can do that a little bit better. I can do, this is XY, right? X1, Y1. This is X2, Y2. How do I find the slope? So what's Y2? Give me an estimate here. Kind of hard to see. 0.02 sounds good. I need to write this down here. 0.02 minus what's Y1? 0.06. And these are units of what? Molarity. Molar. Divided by, what's my X2 and X1? So that's 20 and that's 20 and 10. So 20 minus 10, and that's those units are seconds. Okay, so then what's my rate? So negative 0.04 molar per 10. So what's that when you divide? Sorry, I'm going backwards here, okay? What's that what's that change over time? Negative 0.0, right? Or 0.004 per second. And this is in reference to who? Say again? This is in reference to the reactants because it's negative, right? And so we shouldn't be talking about products because products are being formed. But at that same time, assuming it's 1-to-1, what's the formation of products over time? Positive 0.004 molar per second, assuming it's 1-to-1. But if it wasn't 1-to-1, let's say it was 2-to-1, 2 products for every 1 reactant, 2 products would be, yeah, so you put, or so you said 0.008? Yeah, so 2-to-1 versus this would be 0.00 molar per second. This would be 0.008 because the products would be forming doubly as fast, so twice as fast. 0.008 molar per second. But you need to see the stoichiometric relationships of the balanced chemical equation. Yeah.
I have a question on the graph.
Yes?
So if it starts with 0 reactants, how is it reacting so rapidly?
It's starting with
I'm
0.2.
going up.
Oh, this is not. So these are products for me.
Oh, okay.
Sorry, I tried to label this graph here as products. So the reactants are reacting and they're forming products. Reactants are reacting, they're forming products, and so forth. So yeah, good question. I didn't really label that well. That's concentration of products over time. All right, this is my last part here. Another graph. Same graph actually. Hold on. This graph. Could you, from this graph, without even looking at the reaction itself, could you tell that those are different slopes at different times? I don't know if it's a little hard to see because I can't see the entire graph right now. I'll just do this. Can you see that green line and the red line are at different rates? Okay, so H2 is what this one is, going down. And then HI is the other graph. It should be increasing twice as fast because of this ratio. Right, so we'll do some more work with graphs. You don't have much, I was going to say rate law purposes, I don't think we're going to be able to do that. You have corrections due on Monday. I was looking pretty light. It's nice. But in terms of wrapping up a couple more things that I want to do today, there are some packets here. Kinetics all screwed up. Okay? And you guys are going to complete the trials, record your data, and graph. And what you don't finish from this will be what you finish your homework, okay? You need to collect your data today. Choose groups of 3. Let's do groups of 3. If you want to do a group of 2, that works, but I only have 5 baggies. So groups of 3 would be greatly appreciated. There might be 1 group of 4. Come grab a packet. If you're doing a packet, all screwed up. I'm going to let you read it, and then ask me questions after you read. You got to go to a lab station. You need a timer. You need a baggie and a timer. All right, partnerships, come and grab a baggie for me. Oh, it's not back. All right, I got 2 more baggies. I'm gonna do Oh, I get it. For now, yeah. I need you guys Navigating class, you guys will have to put your laptops up, but just make sure you do that for me.
So there's going to be strong. Alvin, you would
Okay, I'll be the time. I'll be the No, Emma. So wait, is that what happens? When you screw up, how fast you screw it? So it's halfway. You go halfway and then two that. It's like if it takes 2 seconds to get and then I go and take But I stopped the watch. Alright, I got it. Let's start. Alright,
You guys don't have to do it again, it's really not the end of the world.
Get one screw in that ring set. It's a ring set. I hate string tunnels. Get out of It's gone. 13.9 seconds. You don't. No, you don't. No, you don't. Record the time. Like I said, look. What is that you're talking about?
He said go.
So guys, are you guys in the middle of a trial? No. Are you willing? Let me use some segregation. Maybe chemistry, here we go. So you have an entire graph, which is an elapsed time, right? You can see your graph, it goes up to like 150 seconds or 120 seconds. Elapsed time is going to be the final time at each transition of I've made the combination, right? So before you took 1 second, and then now it took 3 seconds, and then it took 14 seconds. That to the third dot you're going to be graphing, that was what, 17 seconds. So you need to determine each one because that's where your individual dot will go, right? So you will have one person be the timer and just before the time when you're done, you can do
Oh, okay, I know where
because if not,
Yeah, exactly.
we were taking.
Like that's what we thought we had to do.
I'll record time. You guys just have to make it. And then I'll just
Start.
Alright. Ready, set, go.
No, he doesn't even know. It's just awesome.
I'll go back to you. Not really. I've seen you.
Alright,
I got it.
come on. Like somewhere to get right on.
There.
God, group mates. He's like hardcore into this. Ready, set, go. You said it before. I'm kidding. Alright. It's error. No, we just error. You don't want error. I tell them to start. Ready, set, go. Alright, I'm gonna do extra Alright. Ready, set, go. All right. Ready?
raise your hand when you're ready for trial 2.
Ready, second. Oh, like sure.
That was good.
20 seconds.
7 seconds. That's a record. That is a record.
Oh, go. Here, I'm on my fire. I know, it's not correct. Ready, second.
Make sure you read, make sure Guys, you have 10 minutes to get the second trial done, so
Second trial. Untrue. Okay, listen. You have to screw it up, screw it half around, and then you take the knob right. Okay. That's fun. It must be dropped back down. I'm gonna keep choosing nothing until I find Done. Like a baby.
Ready for challenge?
Yeah. Okay, so listen. Hey, shut up. So this time, you have to pick, there's nuts on different sides. Put it back in the bag and choose some powder. Okay. All right. Ready, set, go. Wait. Okay, so you need to say things. So you have to, it doesn't fit. Wow. Then you have to. 13. Ready, set, go. You can put it back in the bag. Allie. Ready? You're the same one. That is a new record. No, you can't. You can't stop it. No, I know, but I have to be ready.
Done.
Okay, ready, go. Shoot, so it would be ready. I'm not stopping until it's out. Wait, shoot, I never said where the straight.
I just had it.
Okay, here we go.
you have to get all your data. Now you can't do the worksheets. We have
Got it. I'm ready.
Yeah, we call it just the ratio.
Pass the time to talk.
You can't get with her.
This is
Done.
Pick it up.
Oh, it like tricks you. It's like, nope, not on the side, let's try the other side, but really it's showing on both sides.
My pile. Jesus, air. What did you do? No! Oh my god.
No, wrong. No, it's done.
Okay, now I'm done. Somebody get their calculator.
So you guys have all your data now?
Yeah.
Okay, so write it Emma. Emma, you're gonna play stuff.
Honestly, I play Alex. Alright, give me a calculator. Emma. I don't want homework.
Guys, all your data needs to be down. We have 3 minutes left.
Oh, wait, it's 2.0. I did, okay.
Do you guys mind helping me put this laptop over there?
What was the first slide?
And then add 40 and 60. Cool. No, so this is
Thanks, Allie. Alright guys, so as you're wrapping up, I hope that you had a pretty easy day. With me. You do need to finish take your data, graph it on your stat, your calculator, be stat plotted up, probably for about 5 days in Kinetics. If you don't know how to stat plot, watch a YouTube video or text me. I will try to walk you through that. Keep your package on Lisa, that's a whole tree. Do finish all the questions on this and corrections for No, I read it.
Yo, I possibly could have.
Oops.
Tell that.